begin. All right, we'll begin this session of the moon. Our first talk will be by Tobin Munsat, and it's titled Overview of Recent Science Results from the CCLDAS Dust Accelerator. We're going to have a timer up at the front of the room so they'll know how much time
they have. Thank you for coming. So as Christine said, my name is Tobin Munsat. I'm representing the CCLDAS team. We are one of the nodes of the NASA Lunar Institute in Boulder, Colorado, at the University of Colorado. The first thing I want to say is that this is I'm not going to be able to give much detail on the various experiments. This is kind of an overview or a grab bag of the kinds of things that we've been doing in the first year. And really, the main point is that I'm representing the work of a lot of different people on our team. We have people at all sort of stages of their careers, undergraduates, grad students, working physicists, postdocs, and principals. A lot of young people are doing these experiments at all different levels. The first slide I need to show is simply that we have a dust accelerator. Mihai Harani mentioned this in his last plenary talk. You can go online at any time and see basically the view that you're seeing now of well, if you go online this week, we're probably not much happening in the lab because most of us are here. But normally you can see a bunch of busy scientists working. You can go to dustcam.colorado.edu, which is a live webcam. We've been up and going for about a year, and so what I'm talking about today is just a mention of the kinds of things that we're doing in this first year of campaign. Just a quick technical description of the accelerator. The dust particles are charged and accelerated by a 3 million volt electrostatic generator run through a beam tube to a target chamber. Along the way, there are various dust detectors and a particle selection unit, which I'll describe in just a second. This overall scheme is modeled very closely after an accelerator at the Heidelberg Max Planck Institute at Heidelberg. And I should mention that we are the beneficiaries of an enormous amount of help by their team, and we closely collaborate with them, trading technical designs and even trading people. The generator is a Pelletron made in Wisconsin. The particle velocities that we're able to achieve are tens of kilometers per second. I'll show you a slide which gives a distribution of the kinds of particles we launch. We do active selection of particles, active down selection, so that we can decide very precisely what the characteristics are of the particles that reach the target chamber. We can launch anything that we can charge. And so the easiest things to launch are metallic particles, but we can also launch plastics or silicates if we can coat them with metal, charge them up, and then launch them through the electrostatic electric field. The sizes that we're talking about are a fraction to a few microns. So here's the slide of the distribution from a little bit earlier on. You can see the numbers along the bottom are a little bit small, but the velocities that we're reaching are up to 52 kilometers per second. In fact, recent experiments we may have had a couple a little even faster than that. Generally, we have a lot of particles in the 5 to 10 kilometers per second range, fewer above 10 kilometers per second, but these days we're reliably getting lots of particles in the 10, 20, 30, 40 kilometer per second range. As Mihai said in his plenary talk, each month that goes by, our technology and our operation of this device is getting a little bit better, and so our distribution of particles is getting a little bit faster all the time. We're also developing some techniques to have better detection of the fast particles, which may actually be in the mix, but below our detection thresholds. Let's see. As you saw on the previous slide, we're launching a whole variety of particles. The launching process is fairly imprecise. A lot of different sizes, a lot of different velocities come out of the source and get launched. So along the way down the beamline, we actively select particle by particle which window of velocity and which window of charge and if you know the charge and the velocity and the accelerating potential, you can derive the mass, which exact particles are reaching the target chamber. So this is just a quick map of the detectors. This is a time in milliseconds, but you can think of this as the path of a particle along the beam tube. So it's detected by the first detector, it's detected by the second detector. It is, this is the triggering of an electrostatic gate, which lets that particular particle through to the target chamber, and then right before it reaches the target chamber, we detect it one more time to make sure that we got what we thought we got. Now, as the performance of the accelerator has improved, this has allowed us to go to the next chapter of actual science experiments, which is really the point of the whole thing. So again, the flavor, the types of experiments that we're doing fall into a few broad categories. First of all, we're looking and assessing the impact products. These might be secondary ejecta, it might be neutral gas, they may be plasma that's produced. One important measurement that we try to make is where the energy goes in each of these impacts. We do that by a number of techniques. An important one is looking at light flash experiments. So we use photomultiplier tube sets to resolve the timing and the angular distribution and the spectral content of the light. And I'll show you a slide in just a second on one of those experiments. We have experiments set up to use miniature ion gauges to look at the neutral content from these impact processes. After the impacts are done, we do a kind of a post-mortem to look at cratering, and also as a chapter of all this, we do instrument development and testing. So I'm actually going to fly through a couple of these. One of the measurements that we make are to look at the temperature of the impact plasma by using the light. And in the interest of time, I'm just going to fly through this and simply point you towards a talk which Andrew Collette is giving in just a little while at 11 o'clock later in this session. So rather than spend any time on this, please just listen to Andrew's talk. We also are looking at secondary ejecta experiments, so we can have impactors coming in, hitting a target. We can look at light flash from the target itself, from the primary impact, but also as the secondary ejecta come off and hit the faceplate of these photomultiplier tubes, we can look at the secondary flash from there. We can again measure the angular distribution. We can do time of flight between the flashes to get the speed of the secondary ejecta. By using fairly simple diagnostics of photomultiplier tubes, we can get an enormous wealth of information out of these. I think Mihai already covered in his plenary talk time of flight mass spectrometry, which we can do to measure the ion content. And so I won't belabor this point, but this is an image that he also showed of an instrument which is actually in the chamber. We're actually doing some of these experiments this week. While some of us are at the meeting, some people are actually doing some more spectra back at the laboratory. In addition to the in situ measurements of the impact processes, like I said, we also do a post-mortem on the evidence of the crater, which has implications in a number of fields. One of the first experiments we did was to look at some of Doug Curry's retroreflector candidates, and we blasted them with particles and did electron microscopy of the impacts, and we will continue those with faster particles as time goes by. In addition to looking at the topology and the geometry of the impactors, we can also do a chemical analysis in the microscope. So we can look at, this is for example, an impact on a foil where there is some residue that is flashed off to the side. We can actually use the microscope to do a chemical analysis, zoom in on any part of it, so we can see what part of the residue is due to the impactor, what part is due to the substrate material, etc. One of the uses of cratering studies is actually to do development of instruments. So, for example, PVDF, which is used as a dust detector, the use of that as an instrument depends on the relationship between the incoming particles and the details of the crater. So this is actually an image taken by one of our grad students, Anthony Hsu, of an impact of one of the particles into a PVDF thin film. And so deriving the topology of this crater is critical to interpreting the signals of PVDF detectors, which are actually in flight now and will be also in the future. Let's see. This is a movie which is made of a composite of a number of electron microscope images taken at different angles, again by Anthony Hsu, just to show you the quality of the data that we can get. And you can see there's just an enormous amount of detail in this image, including both the geometry of the crater and also a number of things a number of ejecta which have come off the side. Again, we can do chemical analysis of that. Some of this work is ongoing. But this is a 1 micron size crater that we're looking at. We can back out the geometry. We don't need to do, uh-oh, now I've got it. Can you help me get the slide back up? There we go. We don't need to actually dig into the crater completely to back out the geometry. We can actually use a stereoscopic reconstruction. So we've actually derived a number of routines to take stereo images and back out the depth profile. In fact, what I'm showing here is a map from a completely different, an algorithm that was developed for a completely different process, looking at plasma turbulence in hot fusion plasmas. But we can actually derive it, we can actually repurpose this for deriving depth profiles. In addition to actually backing out the profile from stereoscopic images, we can actually dig out the profile using a focused ion beam. And there's a poster by Anthony Hsu, which was up last night, and I think will continue to be up, where you can take a look at this. I'm just going to skip through this couple of slides just in the manner of time, but as far as instrument calibration, I do want to just mention that the highest profile instrument that's been calibrated is the Lunar Dust Experiment, LDEX, which is going on to the LADI mission. We've had both the engineering and the flight models in the Accelerator, and I direct you to a poster which is going to be given. It's up already. It's actually just back there by Zoltan Sternovsky. And my last take-home message is that this is a very unique facility, which is right here in the U.S. in Boulder, Colorado. One of our charges in building this as part of the NASA Lunar Science Institute was to be a resource for the community. You are the community, so please think about ways in which this facility can be of use to you, and give us a call. You can contact anybody on the team, and we're very, very open and encouraging of collaborative uses. So thank you very much. I think there's a minute or two for questions I went over, but if anybody has a question, I'm welcome to, I can take it. Yes, sir.
What sort of efficiency are you going to get out to put into it to energy out?
Yeah, well, as a propulsion device, the tank, which is the accelerator, weighs about 5 tons.
Well, this would be in a vacuum. I mean, this is out in space.
Yeah, well, but
tank.
Well, in fact, believe it or not, you actually do need a tank. The high voltage, 3 million volts, is not in a vacuum vessel. It's actually in a pressure vessel, because in order to get these high voltages over this distance, you would actually have surface arcs. So I think you would have to redesign the whole acceleration process. And the point is that what we're accelerating are these very, very, very tiny, micron size grains. So I would imagine, I haven't calculated the efficiency of propulsion, but I can go out